So mutually exclusive events, they have no overlap. We think we have things that are happening, but there's no time, like if you were trying to figure, well, I'll show you in a second which one has overlap and which one doesn't. It's going to make a little bit more sense. But when you are calculating the probability of mutually exclusive and non-mutually exclusive events, you have to think about, am I counting something twice? Is something counted twice? Do I need to take away? Is that going to affect my overall answer? And it's going to make a little bit more sense when we're doing this. Most of the time for mutually exclusive events, these are going to be our OR problems. What's the probability of this or this happening? Like, are they completely separate, or do we have some kind of connection between the two of them? Okay. So we'll do these and I'll show you how easy these are to do, just if you kind of think about them. So we're going to say if these are mutually exclusive, and then we'll find the probability. So a box of chocolates contains 3 milk chocolates, 5 dark chocolates, and 3 white chocolates. You randomly select a chocolate. You want to find the probability that it's milk chocolate or dark chocolate. Can something be milk chocolate and dark chocolate at the same time? Like if you have those situations in there, could you, if you're pulling one thing out, could it be milk chocolate and dark chocolate? No, so there's no overlap. So these are mutually exclusive. So you're going to either get one or the other. It can't be like a combination of both. Okay, so this is mutually exclusive. The milk and the dark, they're not happening at the same time. And then we're just going to see how many milk and dark chocolates do we have over how many total. Remember, for probability, you're thinking about the events over total events. Remember doing that in elementary and middle school? Like how many out of 6 if you're doing dice, or how many out of whatever for your probability. So we're going to see the milk and dark. How many milk and dark chocolate do we have in total? 8. So there's 8. And this is the milk plus dark. Okay, over the total number of chocolates that we have in our box. And that is, how many total chocolates are in the box? 3 plus 5 plus 3, and that makes 11. So the probability that we get a milk chocolate or a dark chocolate is 8 over 11. So there are 8 milk and dark together over 11 total chocolates. Is that a pretty high probability or low? It's pretty high. It's over half, right? Okay. Everybody okay? If you saw that problem, you'd be able to do that. You know, you're going to have to add together the milk and the dark. Okay. All right, let's look at our second one. We have a litter of kittens, consists of 1 gray female, 2 gray males. I'm going to keep track. This has got a lot of stuff over here. So 1 gray female. I wrote the wrong thing. 1 gray female, 2 gray males, 3 black females, and 1 black male. Did I write that down? All good for my situation? Okay. So we are asked to find, let's see what the question asked us to do. We want to find the probability that the kitten that we pick, we're picking 1 kitten out of our litter, is black or a female. Can a kitten be black and female at the same time? Yeah, we have 3 of those in the litter. So it can be black and female at the same time. So they're not mutually exclusive. We do have some black cats that are also females. Okay, so just to know, That's the difference between mutually exclusive and not mutually exclusive. You can't have a milk and dark chocolate at the same time. You can with the kittens. So what I'm going to do is I'm just going to look on my list over here, and then I'm going to see if the kitten is black or female. So I'm going to put a check mark by any situation that has a black cat or a female cat, right? It didn't say it had to be both. It just said it had to be one or the other. So my gray females, okay, that's a female cat. Gray males, am I going to check that one? Nope, that we're only looking for black and female. Black female, good. And then black male, am I going to check that one as well? Black or female, if it's a black cat or a female cat. Yeah. So I picked any situation that had a black cat or a female cat in it. So how many total are either black or female? How many total did I check? Look at the numbers out beside. There will be 1, 2, 3, 4, 5. So there are 5 of our kittens that are either black or female. And how many total kittens are there? There are 7. Okay, so with these problems where they're not mutually exclusive, you're going to have to look, and I'm just looking for this or this. It can be either one. It doesn't have to be both. Okay, so I just went through and checked. That's got that characteristic. That has both of them. That's cool. And that one has this characteristic out of our total number of kittens. Thumbs up on mutually exclusive and not mutually exclusive, and how to find the probability numbers. Okay. The reason that we have different names for them is if I couldn't actually see the words and I was just given probability numbers, there's a formula that you use that's different. But all the ones I'm going to give you are going to be situational problems like this. The next thing that's going to happen, so those first two, you're just drawing one thing. You're drawing one thing out of a situation, and it could be this or this. Drawing something, it can be this or this. But independent events, and the ones that we're going to do next, these are going to be and problems. And if two events are independent, they don't affect each other. Like your outcome of your first situation is not going to affect your outcome of your second. They're independent. They're separate of one another. Okay. It's kind of like rolling a die and flipping a coin. Those two don't affect each other, do they? No. So those are independent events. They don't have any bearing on the other. So your situations or your events, they don't affect each other. So when we have these and problems and the independent events, for us to find the probability, we're going to do the probability of the first event times the probability of the second event. So I'm going to do the probability of and the probability of. So the first one that we're going to do, we're going to flip a coin twice. So our two different situations are coin flip 1 and coin flip 2. Does coin flip 1 change the possibility of things happening for coin flip 2? If you flip a coin and get it heads or tails and then flip it again, did what we get at the first one change what could happen for the second one? No, right? You flip it, oh, that's gone, doesn't matter. I flipped the other one had no effect on it. So they're independent. So we're going to multiply our probabilities together. They have no effect on each other. So our first one says the first flip lands on heads. So we're going to do the probability. This is how you say probability of. I'll just tell you the shorthand here. The probability of getting heads. This means prob of heads. That was our first one. I said feds. There we go. And our second one, we want to do tails. So we're going to do the probability that we get tails in any random coin flip. Probability of heads times the probability of tails. Those were our two situations. Heads, tails. They don't have any bearing on one another. So if you flip a coin, what's the probability that you're going to get heads? How many sides of the coin are there, first of all? What are our total number? 2's our total number. How many of those sides is heads? 1. Okay. So 1 out of 2 is the probability that we're going to get heads. Is it the same probability that we're going to get tails? Yep, there's one of the sides is tails out of 2 total sides of the coin. So to figure out the probability that our first one is heads and the second is tails, we do 1/2 times 1/2, and that is 1/4. So there's a 1 out of 4 chance that we are going to get the first one heads and the second one tails. Our next situation, we have a deck of cards. There are 52 cards in one deck. We want to, let's just say, we're picking one card out, then we put it back in the deck, and then we pick another card out. Okay. Did the first card that we pick affect the options we have for our second card? No, because we put the card back in the deck. So there's still going to be 52 chances for that. We want to know what's the probability that both of the cards are diamonds. So these are our 2 events. We want probability of diamonds for our first card and probability of diamonds for our second card. Do you notice how these are and statements? The first 2 we did were or statements. This is both of these, this and this. So we're going to multiply. Both of them happening, that's going to be a multiply, that and that. Let's go ahead and do our bottom numbers of our fractions. How many total cards are in a deck? 52. We're not including jokers in this situation. How many diamonds are there for possibilities? There are 13. They told us there's 13. There's 13 of each suit. Diamonds, clubs, hearts, and spades, right? So 13 out of 52 possibilities for diamonds for our first one. We put our card back in that we picked the first time. So how many options do we have for diamonds now? Still 13 because we put that card back in there. And that is some number that I don't know off the top of my head. This is 169. I know that. 52. And this is 2,704. So the chance that you are going to get both diamonds is 169 over 2,704. Same probability if they said hearts, right? If they said both hearts, wouldn't it be the same probability? Because there's 13 hearts too. Or if they said both spades. Do y'all agree? Have you played cards a lot? Is this familiar to you? The different types of suits and things, different types of numbers. Hopefully they'll tell you this in the statement, or I will on a test, how many cards there are and how many of each type there are to help you out. All right, so those were independent events where the first one didn't change the effect of the other one. The last kind that we're going to do are dependent events, where the first event affects the second. This is still another and problem.
Ms. Rosie, can you scroll back up for like 2 seconds? Okay, I got it.
Okay. So our dependent events is still and problems. The first event is going to affect the second one. And what I mean by that is for like that card problem, it would be like I got a diamond out and then I didn't put it back into the deck. So it's going to change my total number that I have to pick from. It's going to change how many diamonds there are. So we don't have the same total number on the bottom for both of those. So you have to pay attention and think about, oh, whatever I did in my first event has a bearing on everything else. So I need to think about if I need to subtract a number or something like that. And I'll show you. These are really simple to do. You just got to pay attention to that. So we have a basket. It has 5 apples and 6 peaches. So I'm just going to write it out to the side, 5 apples and 6 peaches. You randomly select a piece of fruit and you eat it. Okay. Then you randomly select another piece of fruit. Cool. So we want to find the probability. So our last sentence is always what our probability is. So we want the probability that the first piece of fruit is an apple and the second piece is a peach. So we're going to do probability for apple first and then probability for peach second, knowing that we already had an apple. Okay, because we're going to take that one and eat it after the fact. So let's do our first one. The probability that our first fruit is an apple. How many total pieces of fruit are there in our basket? There are 11. How many of which are apples? There are 5 out of 11. So that is the probability that our first piece of fruit is an apple. What did we do with the apple that we just grabbed? Once you take that apple, we're going to eat it. So we don't have that apple anymore. So what I do over to the side when I'm thinking about my second situation, I no longer have 5 apples. I now have 4 apples. I ate that first one. Do we see how that's going to change our situation? Our first event's going to change our second one because we no longer have as many items in our basket. Okay. Now, one of the apples is gone. How many total items are in the basket now? 10. How many are peaches? 6. And we'll multiply those together, and that's going to tell us the probability of an apple first, a peach second. 5 times 6 is 30. And 11 times 10 is 110. And they'll probably simplify these. That would be 3 over 11, or you could even do a decimal for it. Okay, one last problem. Thumbs up if you see the difference between number 3 and 4 and number 5. Okay. All right, on number 6, there are 6 nickels and 5 dimes. So 6 nickels, 5 dimes in your pocket. You randomly pick a coin out of your pocket and place it on a counter. So we're taking one coin out of the pocket and putting it to the side. Okay, so we have to think about that. So that one's going to be gone once we take our first coin out. Then you randomly pick another coin. Okay, so we want to know the probability that both are nickels. That's what we want to know. This is our situation. So that we have probability that the first one is a nickel and the probability that the second one is a nickel. We have to remember that once we get our first coin, we put it to the side and it's not in our pocket anymore to choose from. So what is our probability that we're going to have, the first one's going to be a nickel? What's going to be on the top? What number on the top? 6 out of how many coins? 11. Good. And then I'm going to go back up here, and I picked a nickel, so I'm not going to have 6 nickels in my pocket anymore. How many will I have? 5. So I'm going to take that and change it to 5 nickels. Okay. Now I'm going to do my second situation. Now this is what my pocket looks like. I'm going to see again for nickels, but how many nickels are there to choose from? There are 5 to choose from. And how many total coins are in your pocket? 10. That is also 30 over 110. That's not always going to be the answer. That just happened to be what those were on these problems. So break these down sentence by sentence and see if you can notice, are you putting it back in? And they'll tell you you're putting the card back in, or they're putting something back into the basket once you take it out, or are you taking it out and leaving it out? And in that case, you need to scratch it off from your total list. Okay. Any questions on the probability? Y'all good? There are only 14 questions, I think, on your homework. There weren't that many of this kind of problem. So you should be able to finish it today in class, no problem at all. And then once you're done with that, you can go back and finish any of the other assignments that you need to do. I don't have your study guide ready yet. I'll have that done today during my prep period, so I can get that finished for you guys. On Tuesday is the ACT Aspire for 9th and 10th graders, so there is no Google Meets for 11th and 12th graders. Okay. Your assignment and the way that you're going to get counted present on Tuesday is to do the study guide. So you have to complete the study guide in order to be counted present for Tuesday. Okay. I'll get that posted this afternoon. You can get it done early if you want. I don't care. It'll be posted for the whole weekend, but that has to be completed. They haven't told us a specific date it has to be done by for attendance, but I would just make sure that it's ready by the test day, which your test day will be on Thursday of next week. So that's the next time I see you is Thursday of next week, but I'll be in communication with you guys through email and stuff. All right, so this test is on sequences, your sequence formulas. You will have your sequence formulas on the test. You don't have to memorize those. Your counting stuff, your P's and C's, and also the probability from today.